Let's start today's dynamical systems seminar, which is currently incorporated into the Simon's semester on invariant structures. It is my pleasure to introduce Spyridon Petrakos from University of Gothenburg, who will talk about quantitative orbit equivalence for Z-odometers. Yes.
Thank you for the introduction and also for inviting me to participate in this semester. It's been very nice. So, yeah, I will talk about joint work with Petr Naryshkin on this kind of latest interest of mine. I come from operator algebras, but this is a purely dynamical thing. And I would say that at least half of the talk, maybe more, will be just introducing quantitative orbit equivalence and a little bit of the history of orbit equivalence in general. This is something that we have seen before, especially in the school in bed level. So let me start by defining orbit equivalence. Of course, we've seen that before. So let's say we have two actions. My groups are always countable discrete. Okay, let them be probability measure preserving actions. On standard spaces, then of course here we have some measure nu and some measure nu, but more often than not I'll omit a measure. This way I will not be dealing with changing the measure and whatnot. So a measure isomorphism. Call it phi. Is an orbit equivalence if it preserves the orbits. So if phi of gamma x equals to lambda of phi x for almost every x, and now I want this to be so if I assume that they're free, which I will from now on, so assume, let's call this alpha, let's call this beta. Then I can define cocycles for my orbit equivalence. So let's say lambda phi from the group times the space into the other group, and let's say kappa phi to the other group, and those will exactly encode how this is implemented. So once I act by an element here on some point in the space, this should be implemented by some group element here when looking at the image of phi. So the exact relation is the following. So phi of, let's say, some s x should be the same as lambda phi of s acting on x phi x. And the same thing, but for the inverse to encode this action. So phi inverse of some, okay, let's say t y should be the same as kappa phi t y phi inverse. Okay, so we have this notion, which is some sort of equivalence of actions that is meant to be weaker than conjugation. And conceptually, it allows us to try to classify things in a more easy way. Because, of course, the conjugacy problem would be nice to solve, but it's typically very difficult to do so outside of very special cases. The problem comes now from the fact that if we care about amenable groups, and since I come from operator algebras, I do care about amenable groups a lot, this doesn't really give you anything. What do I mean by that? There are a series of theorems. So Dye in 1959 proved that any two ergodic transformations are orbit equivalent. So for Z actions we get nothing. And then Ornstein and Weiss in 1980 any two now I can just take countably infinite amenable groups. So indeed, for actions of amenable groups, this relation doesn't.
Free actions.
I mean, what they prove is that any non-singular action is orbit equivalent to an action of Z. Once you go to ergodic ones, you'll get an ergodic Z action, and then they're orbit equivalent by Dye. We usually use the free case, but this is still true.
Yeah, but then you have to assume somehow that the measure is don't have atoms or something like that.
Yes. So.
No, atomic. I mean, that's.
Okay, I was using the. I think, is it the French that usually do this? So I think in the French literature, typically the standardness means the atomless standard. Okay. Yeah, but you're right. To avoid any of these problems, we can just insert freeness, because more or less I only care about free stuff anyways. So for peace of mind, to free. But yeah, it's still true. You have to be careful with what you're saying. Yes. Okay. So once you restrict to amenable groups, you get nothing from orbit equivalence, and even more so, Zimmer in 1978 proved that no free ergodic action of a non-amenable group is orbit equivalent to that of an amenable one. So somehow the orbit equivalence class of a free ergodic action of an infinite amenable group only remembers amenability precisely and absolutely nothing else. However, let me make a comment first that this is really not what happens outside of the amenable case, and it's also not what happens in the topological case. I mean, Karen mentioned in her mini course the classification of counter-minimal systems, and there, even though you only have actions of Z only on counter spaces, you still get a rich classification theory up to orbit equivalence, because it's the topological realm of things. And even on the measurable side, if you go to non-amenable groups, you could even witness rigidity of one specific action. So if you take, remark, this is Fermat. Is it? I think it's 99. So if, for example, you take the action of so then C acting on the torus, okay. Take alpha to be this, then if some beta is even weakly or stably orbit equivalent to this, so if this is even stably orbit equivalent, which is even softer than this, to alpha, and this is, let's say, some gamma acting on X, then gamma is virtually isomorphic to SL and Z, and the action itself is also what he calls virtually isomorphic, which is some specific notion. It doesn't really matter. What matters is that in the non-amenable side, you witness rigidity on a very strongly sometimes. Okay.
And bigger or equal to 3.
And yeah, I guess so, of course. And yes, higher rank stuff. Okay. It's not completely hopeless for amenable groups though, and this we know already from an old result of Belinskaya. So this is from 1968, and I think this is the last really old result that I'll mention. So this gives you nothing. Conjugacy is too hard. What we can start trying to do is imposing conditions on the cocycles to get something in between. And what Belinskaya's theorem tells us is if two ergodic transformations say T and S are integrably orbit equivalent, then either then they're flip conjugate. So either T is the same as S, or T is the same as the inverse of S. Now, what is this? We'll get back to this. It's one specific instance of what very much later was called quantitative orbit equivalence. You just impose some integrability on cocycles, and that already gives you a pretty strong I would say, rigidity result. Okay, so the idea is take something like this and expand it. Try to find other conditions on the co-cycles to try to detect properties of the action or the group. All right. One example of that, before I go into the integrable stuff, is the so-called Shannon orbit equivalence. So, definition. An orbit equivalence phi, as above, is Shannon if all co-cycle partitions of lambda phi and kappa phi have finite Shannon entropy. Now, what are these? So, for every S in gamma, you get a partition of your space, which is by the sets. Okay, this will give you, let's say, a partition S of X, which is X. No, I guess it's of Y. So Y in Y, such that lambda P Y fine is S, and this is indexed over elements in gamma. No, over elements in lambda. So for every element in gamma, you get a partition of your space indexed by elements in lambda, and of course you can play the other game. If you ask for every one of those partitions plus the partitions that you get from kappa to have finite Shannon entropy, as was defined by as was defined in Hanfeng's lectures, maybe I can remind you. So. Entropy of a partition, finite, or coming, doesn't matter, is, well, no, it doesn't matter really. We will not use Shannon entropy, or Shannon orbit equivalence. It's just one example that I wanted to mention. I also went below the line that I wasn't supposed to go. Well, okay, so one thing you can do about your co-cycles is this. And something else you can do about your co-cycles is consider okay, let's say that your groups are finitely generated now. So assume gamma is generated by some finite set S gamma, and lambda generated by some S lambda, and consider two functions, let's say omega 1 and omega 2, from positive reals to positive reals, non-decreasing. definition. We want to use those two functions to somehow determine how fast the cocycles grow. And to do that, let phi as both as before. Phi is omega 1, omega 2 integrable. If for every g, gamma, h and lambda, we can find positive constants. H. That's that. If I look at the integral omega 1, and now I want the norm of the cocycle phi gx over this constant, and I take, so this is with respect to the word matrix that comes from here, so it's gamma. If I integrate this, this is finite, and similarly, if I look at the integral of omega 2 and now I use the other cocycle, so kappa phi h y with respect to this, and I use the constant d nu, this is also finite. The only reason that I'm putting the constants is because otherwise this would depend on the choice of generating set. As soon as you require just the existence of constants so that this happens, this condition is independent. So you're fine. Okay. We have this weird quantification of what's going on. Morally, what this tells you is that, okay, you want to see as G gets larger in its norm, what happens with this cocycle. More or less, you don't want it to go all over the place, because you're varying the x and you're trying to see how H implements the action of G. And you would want this to happen, I mean, ideally in a bounded way, that would be the best. But if not in a bounded way, then at least in a restricted enough way, quantified by this omega 1, so that this is integral. Okay. Now, let's maybe justify why this is a good idea, both the Shannon and the integrable stuff. Why is it a good idea to look at those? Actually, maybe before I do that, let me give you some special cases of that are important. So if omega 1 equals omega 2 equals some omega, we just call it phi omega integrable, okay. This is just for ease of notation. And phi is called integrable if you take for omega to be this, the identity. LP integrable. Now this will give us, this is what appeared in Linskaya's theorem. So the condition there was just that this is integrable. LP integrable for P between 0 and infinity. Actually, you could also take value 0 to mean just orbit equivalence, the plane or classical orbit equivalence, and you could take equal infinity to mean bounded orbit equivalence. But for P between those two, this is just by taking omega to be this. And then you have L less than P integrable. I keep writing integrable, but this is just LPOE, and this is also LPOE. Yeah. Integrable orbit equivalence, LP orbit equivalence, L less than P orbit equivalence. If it is LP, OE, LQ rather, for every Q below P, and finally sub LP orbit equivalent if it's omega orbit equivalent for every omega that behaves in the following way, you want the limit omega over to be 0. Okay.
Excuse me, could you please repeat, when p equal to 0 you get the usual equivalence, orbit equivalence?
It's kind of a convention, let's say, because L0 are just measurable functions, let's say, instead of LP or anything, and asking for any measurable function to do it would just mean, by convention we say that L0 orbit equivalence is just classical orbit equivalence, and then L infinity makes sense again. Of course, I cannot put anything here, but it's not really an integrable condition, but conventionally we say that it's L infinity orbit equivalent if it's bounded. Okay, now I get to why those things are useful by stating some theorems. So first of all, in a paper by Austin, but really the thing that I will mention was in the appendix that was written by Louis Bowen, so I'll write Bowen in 2016. L1 orbit equivalence preserves growth of the group. So if two groups have an L1 orbit equivalence between any two actions of them, they have to have the same growth. Then, let's say Dalaby. Well, I will not write the whole names because it's a big list. So Dalaby, Quevisto, Lemaitre, and Tessera in 23 is what I want to say. Maybe 22. It's a bit earlier, but the publication date is either 22 or 23. I have it noted somewhere. Okay, they proved that more than this, LP orbit equivalence preserves the so-called LP isoperimetric profile. Okay, if you take here the L1 thing, you will recover the Follner function. LP is somehow finer, or it gives you more degrees, but it doesn't matter. It tells you something about the asymptotic geometry of your group. That's the take that I want you to get. In fact, what they prove, here is where they introduce this definition of having asymmetrical notions of integrability. And everything they prove here is typically one-sided. So it only it tells you that, you know, if one side of this is, let's say, LP, then the isoperimetric profile will be asymptotically bounded by the other one. So if you have both LP, then you get something like this. But they get more quantitative control, is what I'm trying to say. And the idea behind having this asymmetric type definition is that, okay, if you're working with different groups, as you want to do when working with orbit equivalence, it's very restrictive and unreasonable to only study the symmetric definitions, because you cannot expect, for example, those two things. I mean, Z will embed, quote unquote, embed here in a much nicer way with respect to cocycles than the other way around. So if you wanted something symmetric here, it would have to be bad because you're trying to also embed this into here, in a sense. So by having this asymmetric definition there, you allow somehow to be precise. Okay, and another theorem by David Kerr and Han Feng. This is 24. If I look at actions of mutually abelian groups, so for actions of mutually abelian groups, Shannon orbit equivalence, so Shannon OE preserves entropy, topological entropy. There are more results connecting Shannon orbit equivalence to entropy, but I will not get into this. I'm just trying to make a point that, okay, on the base level of classical orbit equivalence we get nothing, and then as soon as we start imposing stuff, you can get back some different degrees of rigidity, or you get back some properties of your acting groups. There are also some things that we know that you cannot do. So let's say this is what it does, and now what it does not. In the same paper by these authors, so WB, Cuivistol, Lemaitre, Tessera, finite presentability of your group cannot be recovered, even when requiring, even if you have an exponential orbit equivalence. Of course, the more rapidly this increases, the harder this condition is to be satisfied. So when I talk about exponential orbit equivalence, you should be thinking of a very strict notion of orbit equivalence. So finite presentability is not preserved given by exponential orbit equivalence, and also finite asymptotic dimension. So finite same thing. And in both cases, they construct explicit examples. Here they have a group of asymptotic dimension 2, and then a different group that contains the infinite direct sum of Z, which has infinite asymptotic dimension. So the group itself will have infinite asymptotic dimension. And they construct as nice exponential orbit equivalences as you want between those groups, even though they have one has infinite asymptotic dimension and the other has 2. And similarly for finite presentability, they have an explicit example. Okay, this is somehow the general picture of what is going on for amenable groups and what are the general definitions. Now, ironically, I want to restrict back to transformations and look at some things there, which means that maybe it's a good time for a break, and then after the break I get back to Z actions.
Okay, then a break for 5 minutes, say.
Yes. But you can slow. You can, if you want to go more, you can go more. If you want to stop in between, you can take less time. You can take less time.
Okay, okay.
That's no
Okay, I'll be ready today and then let you know tomorrow. Go.
All right. So, as I promised, I've been talking about this general framework of that works on the amenable side, yada yada yada. But now, for the second half of the talk, I'll just go back to the very basics, back to Z transformations, ergodic transformations, because there we also have interesting questions that are related to this quantitative version of orbit equivalence. So let me expand a bit on the motivation on that side. First of all, let me just say verbally that this somewhat complicated definition that I gave for the general case, well, the conditions that you need to check on the integrals, you can just check them on generating sets. So in particular, when you're working with ergodic transformations, you can just take the natural generating set, which is a transformation itself. So really what you have to check is two things. You don't really have to go through countably many integrals that you need to check. So it's somehow computationally much simpler. Same for z to the d or anything like that. Once you go into concrete stuff, things simplify. Now, some results that are known in the ergodic transformation case. So, say, let P be ergodic and omega be sublinear. Why am I restricting to sublinear things? Well, we had Belinskaya's theorem that told us that as soon as you hit L1, you're already flip conjugate. So you're already very rigid. So you would want to see what's going on between plane orbit equivalence and L1. So you start looking at sublinear things. And some theorems in that direction are the following. So Cardery, Joseph, Lemaitre and Tessera. This has to be 23. I think that's why I confused the other one. They have a paper that is very aptly titled Belinskaya's theorem is optimal, where they show exactly that. So assume that there exists or doesn't. There exists, yes. There exists some n larger than 2 such that Tn is also ergodic. Then there exists some transformation S, ergodic, which is omega orbit equivalent 2t, but not flip conjugate to it. So somehow, when you're going through everything that is sublinear, you're basically exhausting what is below L1. And what they say is that if you stop at any degree below L1 and you have this extra condition, then you can always find something that will be orbit equivalent in that sense. So as close to L1 as you want, but not L1, so not flip conjugate. Now, from this, for example, one transformation that does not satisfy this is the universal odometer. And having that in mind, Correa, I guess it's 25, proved the same, so the same holds for odometers. Okay. But this one side of motivation for what I'm about to say later on. One other side is the following. Hanfeng and David in the same paper where this result comes from, they prove that any odometer, Z-odometer. Here I also mean, of course, classical odometers, so the Z-odometers. Any Z-odometer is Shannon OE, not any, rather every to the universal one. I'll get back to what odometers are, what the universal one is, and what not. To the universal one. This is probably a good moment to mention that even though we call all these things orbit equivalences, not all of these are equivalences. In particular, LP orbit equivalence is only an actual equivalence if P is larger than 1, because you lose transitivity. And for Shannon orbit equivalence, I think it is not known if you get transitivity. So a result like this is really one-directional. You don't get that everything is Shannon orbit equivalence between themselves. It's really pointing towards the universal one. And Correa in a different paper, same year, strengthened this to changed. Do we have color? We do. Okay. I have some here. That's fine. So Correa. The same, but here you replace Shannon with L less than 1/3. Okay. Which is still one-directional because, again, orbit equivalence below 1 is not an equivalence. You don't get transitivity. Okay. Now, why is this a strengthening of Shannon? What we have is the following picture, let's say for Z transformations. So here, let's say, is conjugacy. Here is orbit equivalence, which is trivial. Okay. Let's put Shannon somewhere here. So Shannon. Then if you put here log integrable, log of E. This is stronger than Shannon orbit equivalence, and of course this will be stronger. So now you have, and somewhere here you have flip conjugacy, so L1. Flip conjugacy. By the way, those two things are not the same. In the measure preserving case, there is a paper by it's a Japanese guy from 1951. I'm not sure if it's the first example, but it is one example. And given the fact that the paper is titled "An example of something that is flip conjugate but not conjugate," I would assume it's the first one, but I could be wrong. So it's not very easy to describe an example, but they exist. Those two things are not the same. And then in between here you have all the other integrability degrees between log and L1. Going for higher LPs does not really give you more than flip conjugacy. It is still useful for growth and whatnot. Well, not because we're talking about. It's useful in general, but for Z transformation, it's not really useful. So you somehow live in this realm of orbit equivalences that either are known to not be equivalences or it's unclear, which makes it more difficult to somehow work with them. And being interested in that, Peter and I. Well, okay, maybe I'll first explain things that I've mentioned here. So, odometers. Odometers. There are several equivalent pictures of what an odometer is. I'll give two one for practical reasons and one for because it's the one that we are using. So one way of thinking of odometers is thinking them as adding machines. That's the typical way that you would introduce them, I guess, in an ergodic theory course. So on one hand, they're adding machines. So think of Z acting on, you have here 0 through, let's say, Rn. And you're acting by addition with carryover. So you go, so what would you do if you have a tuple? You try to add one here. If you're anything below Rn, you just add one, you're done. If you are Rn, so anytime you have the maximal, let's say, degree here, at some point this will stop, except when it doesn't, but okay, let's say it stops. So here you have something that is not maximal, let's call it K. This will be mapped to just 0, 0, K plus 1, so on and so forth. Okay. And of course, when you have the maximal string, so when everything is Rn, you just go to everything being 0. So that's what I mean by an adding machine. A different way of seeing this, and one that is useful for the proof later. Oh, the measure, of course, here, I mean, this is the, you can see this as a topological dynamical system, but we're interested in measurable stuff. So here you just have the product measure on those faces. Now, an equivalent definition that is very believable to be seen that is equivalent is the following. Consider some sequence Kn of natural numbers. Let's say strictly increasing, so increasing, such that everything divides the next one. Okay, then you can consider the finite dynamical systems. Everything is acted upon by Z, just by shifting, so consider K0, Z, and then we just have the modulo map. You equip everything with a uniform measure. You're acting here by shifting, and you can take the inverse limit of this thing, and this will give you an odometer again. And of course, with this notation there, Kn would just be the product up to n of the Rn, of the Ris, I guess. Did I start from 0 there? No, I started from 1. Let me correct that. The 0 is very much a natural number. Okay. If you do this, then you end up in the same situation you can see the correspondence. And it's somehow very easy to classify odometers, very explicit, let's say. And how do you do that? What you start doing is, for every for every p prime, consider the limit of n goes to infinity supremum, limit of the supremum, or max really. Well, supremum is the same. Okay. Call this kp, or no? I've used r there, huh? That is okay. Exponent p. Fine. This will be the limit of the supremum of the times that pk divides kn. Okay. This is a very complicated way of just saying, start going up those kns and keep track of what divides them, the prime decomposition of them. If you take the limit, you will end up with a supernatural number. And this supernatural number completely determines the odometer, both topologically and in the measurable way. So this will give you, so product over P of EP is a supernatural number. Okay. No, P, EP, sorry. Natural number. And this is in bijection odometers, with odometers. I think the classical way of proving this is using the Helmholtz-von Neumann theorem, because odometers have a discrete spectrum, and the spectrum comes from this supernatural number, and the Helmholtz-von Neumann theorem tells you that discrete spectrum transformations are classified by this spectrum. But you can also prove it using the Giordano-Putnam-Skau technology. You can use Bratteley diagrams and prove it topologically. Okay. Now, we know what an odometer is, we know what's going on there. The universal one, universal odometer, corresponds to every exponent there being infinite. So okay, good. So now, what Peter and I started looking at Naryshkin. Initially, when we started this project, we were only thinking of even those specific results to try to make them bidirectional. I mean, you don't get, everything is pointing to the universal one, but we wanted to show that it actually points between everything, as with having in the back of our minds trying to show that to justify that this should be an equivalence. as I said, we don't know, as far as I know, we don't know if Shannon orbit equivalence is an equivalence, and we were interested in this, so we tried to look at this very specific class. But it turns out you get a lot more. Namely, you get the best possible bound you can get. So any two Z-odometers are sub L1 orbit equivalent. Why is this the best you can ever hope for? Because as soon as you hit L1, your flip conjugate, and for a discrete spectrum, that's the same as conjugate. So somehow, even when you look at this very kind of expanded picture for orbit equivalence, for odometers in particular, everything collapses. You're either trivial, so either not related at all, or conjugate. Even when, even when looking at this very refined, let's say, type of orbit equivalence. All right, and how does one approach this? The proofs of these things here, everything that I'm going to say, both for this and this, are all constructive. And somehow here, you use the fact that the universal odometer has infinite exponents, which allows you to have some flexibility on one side of what you're trying to show. And you're very careful with what you're doing with the other odometer that you started with. Same for the other results. So somehow to do this, you want to take into account both odometers that you started with, both systems. And for this, we use the inverse limit picture in the following way. So what you want to construct is some orbit equivalence, and you want to somehow have cocycles that do not grow very fast. So the idea is to somehow control it locally on the intermediate steps, and then construct some limit map via some intertwining, and this should do the job. What do I mean by this? So let TS be odometers. We will construct some sequence Kn such that the odd, so T should be the inverse limit of, let's say, the even ones. So okay, and maps, let's call them phi n, from, I think, yeah, let's say if you start by phi 0, okay, this will go from z k n plus 1 z to z k n z, which hopefully will give you a limit at the end. Somehow when I give this talk in front of Pareto algebraists, they naturally think of Elliott's intertwining arguments and things like that, which is very natural, and it should have been what I I should be thinking about when doing this, but instead we were mostly inspired by Keenan-Smorodinsky's proof of finitary Ornstein's theorem. But okay, you'll see what it reminds you for yourselves. So the picture we have is K0Z, K2Z. It's just a mod map. No, the other way around. Sorry. Okay, and here we have X being the one odometer, and say Z, K1Z, V0, V1, okay, K3Z. All right. Now, what will these maps be? These maps cannot possibly be on the nose compatible with this whole diagram. Maybe 5 inverse. Something like this. This will never be on the nose commutative, so that you directly invoke inverse limit behavior. But the idea is to make it approximately commuting up to an error at its level that will end up being summable, so that you can invoke Borel-Cantelli and say that, okay, it's not quite commuting, but up to measure 0 I can define something. And also, preserving the measure will also not happen on the nose, because the spaces are not really compatible. But again, you can make sure that they're measure non-increasing, and because you have an intertwining, measure non-increasing on both sides will end up giving you measure preserving at the end. And in order to do that, it really boils down to correctly choosing your kns. You want them to more or less increase rapidly. And how rapidly is that? Well, you want somehow Kn to be much larger than the product of the previous two. And why do you want that? Because the way that we construct these maps is as follows. So, before defining phi-ns, we construct some auxiliary maps on these products. So, construct auxiliary psi-n. Let's go from these are self-maps of the interval k n minus 1 and kn minus 1. Okay, and how do you define those? I'll do a picture instead of writing things, and maybe I'll use color again.
Excuse me, could you please remind whether kn plus 1 should be divisible by kn in your construction?
No.
Okay.
No, that is the point. I cannot assume that, because the supernatural numbers of the two odometers can be completely disjoint in the sense that, nothing divides nothing. And that's why here you cannot really expect actual measure preservingness or commutativity of the diagram. But as soon as you do something like this, you get approximate divisibility. And that's the trick somehow. So what is this auxiliary map? Those will be defined inductively. So what you do is, okay, you have this interval, let's say, through here. Now this is separated into blocks of size kn. And so on and so forth. Let me put some dots here because the interval is very long conceptually. So now, okay, this is exactly divided into blocks of size kn. Maybe put one here. And then inside this block itself is further separated by blocks of size, so this will be kn minus 1, kn minus 2. Because remember, we'll make a choice of this kind. And now this will not exactly divide this interval. You will have some remainder here. So, color, have some green there. So at the end of its interval, you have some remainder that comes from dividing kn by this product. And now you have the same picture below. So on and so forth. But now what you want to do in terms of mapping is put all the remainders from these blocks at the end here. So you have, I don't know, a bunch of them. Maybe the remainders start here and you have remainder, remainder, remainder. Probably lots of them. So all of these are remainders. So the map that you do is the following. And the rest of it is just kn blocks, not kn, product blocks like these ones. So those are all the same size, supposedly, and those are all the remainders, which are the same size as this. And now what you start doing is just start at the beginning, map this one down here, map this one down here, and so on and so forth. And the remainders also, in order, map them at the end. So this there, this there. But you cannot naively just do that. This will preserve nothing. This mapping here will actually be the identity, so this you do naively. But here, as I said, this is an inductive construction. Here you use psi n minus 1 inverse. This is of the correct size. It's again a product, the interval of length, the previous product, so you can apply the inverse of this. Of course, at stage 0, you just use the identity, but later on it gets more and more complicated because at each step, you take all you take the new remainders, you put them at the end. You take the remainders from the previous step and take them from the end and put them back where they were. And then from the previous step, you do the other way around and so on and so forth. So things are moving around all the time. But even though they move around all the time, the point is that for most points, if you try to see what the cocycle does, so if I move by one step up here, whatever the one step is, it's a very small arrow. If I move by one step up there, no matter where I do that, for most points, I will only move by whatever this was moving me. For some points, I will just move by 1, which is the ideal scenario. Moving, like, whenever I move by 1, if I still move by 1, that's the best cocycle you'll ever get. And then you have some points that get moved by a lot, which are the points where you change. So when I jump from here inside the remainder or from the remainder outside, I have a big jump here. That is true. But I can make the set of those points be as small as I want. only governed by the divisibility here. So if this is huge, this will be approximately very divisible, and I can make this as small as I want. So once I have these auxiliary maps, I can define my phi n to be the following. So phi n was from, where was it? So it starts at this, kn plus 1. What do? I first project using mod onto the product, so z kn minus 1 z. Then I use, sorry for how ugly this is, okay. Then I use the inverse of this new map, the auxiliary map, which keeps me inside here. Kn minus 1 z. And then I project down to where I need to project, which is this. So another mod map will bring me to z kn z. Okay, so now I have the phi n that I wanted, and somehow, since if you construct this carefully enough to make the local cocycles here behave very nicely, then the cocycle of this thing eventually, again up to a set of very small measures that will be summable at the end, the cocycle of this thing will agree with the cocycle of, I agree after projection, with the cocycle of the auxiliary map, so you get good cocycles. And at the end, by the way that we constructed this thing, you do get approximate commutativity of this diagram. And this will give you maps here. The cocycles of the induced maps will be pointwise limits of these things. So you just use Fatou's lemma, and whatever bound you had here for the integral will pass here. You get measure preservedness, again by this approximate, by the fact that everything here is approximately measure increasing. And yeah, and of course by construction, this will send orbit to orbit. Okay, that's a very rough sketch of what's going on. So this gives you this theorem. In fact, if you start with your favorite sublinear thing, you can really, in fact, for any epsilon and omega sublinear, you can obtain the integral of this thing to be as small as you want, as close to the value of this as you want. Of course, you will at least get this, but it's really as optimal as it gets. And now the question that arises is, can you use the similar techniques, or maybe other techniques with a similar flavor, to get more than odometers? There are two natural candidates for this. One is, so question 1, what about rank 1 systems? Of course, you cannot expect to do this in full generality. I mean, some of those are not even, they don't even support an invariant measure. But let's say you restrict to some nice enough class. For example, Correia has this what he calls flexible classes of rank 1 systems, and those are great candidates to use here. And in fact, we were thinking about this a bit. If you manage to prove something along these lines, you can remove, I don't have it anymore. There was this theorem of optimality for Belinskaya's theorem, but it required to have some power that is still ergodic. You can remove this condition if you prove something of this flavor. There is a trick that you can do. So this is an interesting question. And another one that I think is not necessarily more interesting, but certainly more in the spirit of what's going on here is the following. For z actions, we know that somehow the absolute bound of orbit equivalence that you would ever get is 1. It's Belinskaya's theorem. But for actions of zp and zq, there is also a bound. So fact or theorem, I don't know. Dalabi, blah blah blah, Lemaitre here. If I have two actions of Zm, free ergodic, the usual stuff, are at most L or sub L, what do I want? Ln over m, L m over n orbit equivalent. So we have critical bounds for actions of z to the d for different values of d. And in fact, Correa has managed to prove that you never actually achieve the critical value. So it's really at most sub this thing. It was a question of whether you could actually get this at some point. You cannot. What is even more interesting is that somehow, if I look at the dyadic odometers of those things, they do satisfy this. They have the optimal integrability conditions. So the natural question here is, are all, let's say, Zm Zn odometers, do they achieve this optimality there? So sub L M, is this correct? Yes, it is. L M and OA. Of course, things become more tricky because in our proof we very crucially use the geometry of Z. It's just a line. You can work with it much more easily than you can work with squares, especially squares of different sizes. But I don't think it's hopeless. It just needs some care, maybe some new ideas, but not necessarily too far from those. And yeah, I think I'll stop here.
I have a question.
Yeah.
I missed, so concerning question 1, do you have generalization to this case, at least for some systems with some very strict conditions for uncon systems?
So this is something that I'm actively thinking about. In fact, I started working with Cohentin numbers like a week ago. So not yet, is the answer. We're hopeful, but nothing yet. What would be nice to get here is something that has something irrational in its spectrum. That would be a nice start. So something like an irrational rotation or something like this would be great. Because this would give you the the optimality of Belinsky's theorem without the restriction already. That is a very specific, let's say, subclass of rank 1 systems. But yeah, conceptually, this should be doable for a larger class, because here you also have inverse limit pictures. They're not as nice. I mean, in the same way that, you know, the tower decomposition of an odometer is perfect, and of a rank 1 system it's not. But if you start imposing conditions on the spacers, so they're not like too, they don't explode too fast, I think this is doable.
But in your construction, is there kind of argument that if you add some tiny spacers, carefully chosen sizes?
I think it should still be fine, yes, because you can somehow throw them into this whole mixture of Borel cantilis and just throw them out. But of course you cannot always do that.
With respect to the second question, so for example, in the case of the topological orbit equivalence, so for Z-odometer, everything, I don't know, if you have two Z-odometers and they are orbit equivalent, so they are conjugate.
Yes.
But for C2 odometers, this is not true anymore. So you have things which are orbit equivalent, but they are not conjugate. Or you have also this property that the continuous orbit equivalence is not the same than flip conjugacy. So I don't know, I wonder if you can relate, for example, for question 2, these measurable notions with the topological notions of orbit equivalence, at least for the case of odometer.
I think it might be difficult because already, I mean, even for Z, the connection doesn't work. Because again,
at least for odometers, everything is more or less trivial.
yeah, exactly.
For C2 odometers, for example.
I'm not sure, is what I'll say, because I don't know how good of a picture we have of what a Z-squared odometer looks like. I mean, for Z, you have your supernatural numbers, you can play around, everything is very clear. Already for Z-squared, this is trickier. So finding a connection, obviously, as I come more from topological dynamics and sister algebras and things like that, I would love for a connection. I would feel more comfortable with a connection, but I don't know.
So what about if you consider the product of two odometer actions as Z2 actions?
The product of two odometer actions
As
is...
Z2 actions?
Oh, you mean... yeah, okay. This is, when I refer to dyadic odometers here, what is called a dyadic odometer in this case is exactly taking the product of dyadic odometers. And this, I mean, the dyadic ones, they do get the optimal stuff, and I believe that, yeah, in this specific subcase of an odometer, you would still get it, probably with very similar arguments. Similar arguments, not to ours, but to theirs. Our arguments are a bit overkill, I would say, when you look at, when you already have some compatibility on the odometers. Although, no, you would actually need some combination of the two. Somehow, yeah, because you didn't want them to be of the same. Like you wouldn't take one to be, I don't know, dyadic times dyadic and the other being dyadic, and I don't know, cubic and whatnot. You want them to be whatever, right? In this case, this would not necessarily work. Regardless, yes, in this special case of odometers that come from Z-odometers as products, I expect things to be much nicer. But of course, then it's maybe less interesting. It's a good test case. I mean, if it fails there, it certainly fails in general, but I don't expect it to fail.
If no more other questions, let's thank Spyridon again.